Hello and welcome to Science. Today we're going to be continuing with the equilibrium part of the 12a topic, so you should be able to use this to help fill in those workbacks. I'm going to be doing dynamic equilibrium today. So last time we were having a look at the reversible reactions, and now we're going to have a look at a bit more detail about how that actually works in practice. The easiest way of showing this is through drawing a few little graphs. So here we go. So what we've got here is a graph, and on the x-axis we've got time as time goes on, and on the y-axis we've got the amount of reactants and products, with all of it at the top and none of it at the bottom. So in a standard reaction, a non-reversible reaction, you would start off at 100% with your reactants, and you would end up at 0% as it was all used up. And your products would start at 0% because you didn't have any, and it would end up at 100%, assuming a complete yield. In a reversible reaction, it's slightly different. So what we'll do is we'll use this purple line to show the reactants. So, look at the focus. It starts off at 100%. Okay? And over time, as the reactants get used up, the concentration falls. Okay. Now for the products, so I'll label that line R for reactants. Now the products start at 0% because you don't have any right at the beginning, and then they gradually increase, and those are the products. So we'll label that line for P. Now you'll notice that neither goes all the way to the top and all the way to the bottom. Once these lines go completely horizontal, so that's about this point here, we call this the point of equilibrium. That's the equilibrium reached. Now, it's really, really important to know that at this point, the reaction hasn't stopped. It hasn't finished at this point. The products are still turning into reactants, and reactants are still turning into products. It's just that they're happening at exactly the same rate. So overall, there's no change in percentage, but it hasn't stopped. It's still going. It's still keeping on going. That's a really important point to take on board. Another really important point to make is that this only works in a closed system. And so that's why in the experiment that it showed in the last video, we put a cotton wool ball in the end of it to stop gases escaping. Because if we look here, if we removed the products here and went down, what would happen is that this would then continue and it would find a new equilibrium point. Now, if it's constantly being removed, as in an open system, it would appear like it was a completely irreversible reaction. But in a closed system where things can't get in, can't get out, it will reach this equilibrium point. So for our exam style question, I've put down an equation here, which is calcium carbonate, and with heat, decomposes to make calcium oxide and carbon dioxide. Okay, and the conditions are that it's in an open test tube. Exam style question would be: explain why equilibrium will not be achieved in this case. So I'll give you a few moments to think about that, and I'll give you some hints. So the hints for it are: it's not going to be forming an equilibrium because it's an open test tube. So that if it's an open test tube, it means that gases can escape. Okay? So now the next point is that because you know gases can escape, you have a look at your equation. Do we have any gases involved here? Yes, we do. This carbon dioxide is a gas. Because the carbon dioxide can move out of the test tube, it means that you haven't got all the ingredients to reform our original reactants. So it can't form a dynamic equilibrium. Cheers.